Welcome to this next video in the playlist on group theory. In this video, what we're going to do is define the concept of the index of a subgroup, and we're also going to have a look at an important result relating to the index of a subgroup. Okay, so let's begin with the definition of the index of a subgroup. Okay, so what we're going to need then is some group, capital G, to be working with, and this group can either be a finite group or it can be an infinite group. So we're not limiting our attention down to just finite groups. It can be an arbitrary group, capital G. Okay, it doesn't need to be an abelian group, it's just an arbitrary group, capital G. Okay, and now let's say that we've got some subgroup of G, which we'll call capital H here. So H is a subgroup of G. Okay, and again, this is just an arbitrary subgroup of G. It doesn't need to be anything fancy. It doesn't need to be a normal subgroup, for instance. Okay, it is just a subgroup of G. Now what we're going to define is the index of this subgroup capital H in the group capital G, and for short this is written with modulus symbols around the outside, and then inside you put G colon H, like so, and then you complete the modulus symbol. So this should be read the index of H in G. Okay, so whenever you see this symbol like this, you should read the index of H, the subgroup H, in the group capital G. Okay, so what is this? That's the notation for it, but what actually is it? Well, it's the number of left cosets of the subgroup capital H in the group capital G. So let's draw a picture for this. Okay, so we'll have our entire group capital G denoted by this box here. Okay, like so. So I will colour in the entire group capital G in green, or at least outline it in green. So this is our entire group. So of course the box just represents the set of symbols that form the group. Of course, apart from just the set of symbols, you will also have the composition law defined on it, which this picture doesn't show, but we're assuming it will have that. Okay, this is just a picture showing the set of symbols. Okay, and then what we'll have is the subgroup capital H down here. So let's say this is capital H, which of course is a subset of the group capital G, with the fancy property that if you restrict the composition law on the entire group down to this subset, then that subset with the restricted composition law actually forms a group in its own right, and therefore it's called a subgroup of capital G. Now, what we know is that for an arbitrary group for an arbitrary subgroup capital H of the group capital G, what you can do is you can use it to partition up the group into either left cosets or right cosets. Now I want to stress, you can do this for any subgroup. You do not need the subgroup to be a normal subgroup. This is a common misunderstanding, that in order to partition a group up into cosets, you need to have the subgroup as a normal subgroup. Indeed, if you have the subgroup as a normal subgroup, then the left coset partition and right coset partition will be exactly the same, whereas they won't be in a more general subgroup case. What's more, if the subgroup that you're using is a normal subgroup, you can actually define a beautifully well-defined composition law on the set of cosets and therefore form the quotient group. But just to partition up your group into a left coset partition, you do not need your subgroup to be a normal subgroup. Okay, with our arbitrary subgroup capital H here, I can partition my group up into a left coset partition. Okay, so what you'll do is you'll construct left cosets, and I'll just try and draw on 8 here. So we'll firstly quarter it, and then I'll split it into 8 different pieces. So that one needs a line coming down it. How many have we got now? 1, 2, 3, 4, 5, 6, 7, 8. That looks a little bit uneven. Okay, I'll just imagine they're all the same size. I didn't manage to get the picture perfect, but imagine that they're all the same size there. Okay, and then we've got 8 of these cosets, left cosets of the subgroup capital H here. Okay, so in this case, in this picture, the index of the subgroup H in the group capital G would be 8, because the number of left cosets that you formed here of this subgroup is 8. Okay, so let me just remind you of how left cosets work. So this left coset here of the subgroup H will be generated by some element that's in it. So let's say there's an element little a in here, and you can take an arbitrary element in here and use it to generate the entire left coset in here. And the way it's generated is you just multiply all the elements of H, the subgroup H here, on the left with this element A, and of course you're going to get loads of answers, loads of different answers, and you'll get a different answer for all the elements of H. That will give you a subset of the group capital G. All of the elements will be outside of the subgroup capital H, and what's incredible about this is if you use any different element of the left coset of H under the element A to generate a left coset. So if you, for instance, took another element in this left coset and used it to generate the left coset under H, it would generate you the exact same set, and that's what allows us to build this well-defined left coset partition of the group, that any element of a left coset generates the exact same left coset. So truly, you do build a well-defined partition. And then, of course, you'll have these two cosets here, the subgroup H and this first left coset, and then you'll either that will cover the entire group, or there'll be some element outside of it. You can then generate its left coset, and again, if that element that you used to generate it was outside of the previous two left cosets, then the entire left coset that it generates will be completely outside of these two previous left cosets. And again, it will have the nice property that any element of that left coset will generate the exact same left coset. Okay, so there is this well-defined partition of the group into the left cosets of any arbitrary subgroup capital H, and all you need to do in order to find the index of a subgroup, or indeed all that's meant by the index of a subgroup, is how many of these left cosets do you actually get when you partition up the group into the left coset partition of this subgroup. Okay, so there you are, there's the definition of the index of a subgroup in the group capital G. Okay, now a little bit more nomenclature then. So the answer can either be finite or it can be infinite. So you can either end up with a finite number of left cosets here, or you can end up with an infinite number. Of course, the finite case is nicer, it's easier to work with, but the infinite case is also a possibility. Okay, so if the subgroup has finite index in the group capital G, then we say that the subgroup has finite index in the group capital G. I know that's just repeating myself, but if this number comes out to be finite, we say that the subgroup has finite index in the group capital G. Whereas if this number comes out being infinite, then we say that the subgroup has infinite index in the subgroup capital G. So there's a little bit of notation to be aware of. Okay, the other thing to say is if the group capital G is finite, so let's now work with it being the case that the order of the group capital G is finite, then this becomes much simpler. So if we know that the order of the group is less than, let's say, infinity, so it's finite, then what can I say? Well, of course, I know that the index of any subgroup in a finite group has to be finite. Okay, I hope that's obvious. If the group is finite, then how can you possibly get an infinite number of left cosets in a left coset partition for a subgroup of it? You can't, is the answer. Okay, so if the order of the group is finite, then of course any subgroup will always have finite index within that group. So the index of any subgroup H in this finite group capital G is always going to be finite. And we can actually say more. I can actually give you a beautiful formula for working out the index of the subgroup H in the group capital G. Okay, so how can I actually work out how many cosets, or rather how many left cosets of H there are going to be in the left coset partition of the group capital G? Well, each of the left cosets is going to have the same size as the size of the subgroup, which of course will just be a finite number in this case because the order of the group is finite, therefore the order of any subgroup is also going to be finite. Okay, so all of these left cosets will have the same size as the size of the subgroup here. So if I want to know how many of these cosets I'm going to have in the entire group, all I need to do is take the order of the group and divide it by the order of the subgroup. Okay, because if the order of group is finite, that's how many elements you have in the overall group. If in each coset we have the number of elements in the subgroup here, i.e. the order of the subgroup, then all we need to do is divide this by this to work out how many cosets we're going to get, and indeed that will be the index of the subgroup H in G. Okay, so if you're working with a finite group, capital G, then this formula holds. Of course, if the group is infinite, then this formula doesn't hold. Okay, so it's very nice and easy to work out the index of a subgroup in a group, capital G, if you're working with a group, capital G, that is finite. Okay, so that's a nice theorem, and of course, this formula here gives rise to Lagrange's theorem, which we've seen in previous videos in this playlist on group theory. Lagrange's theorem, remember, states that the order of a subgroup must divide the order of a group, and this is exactly why, because any subgroup must have a whole number of cosets, of left cosets in the group, capital G. The index must be a natural number, and in fact that's something I maybe should write here. It must be a natural number, a counting number, 1, 2, 3, 4, 5, etc. Or of course it could be infinity, so maybe I should add the natural numbers union, another symbol here, infinity, which just means that there is no natural number that is the number of cosets you've got there. Okay, so it's unbounded how many cosets you've got there. Okay, so those are the possibilities. It's a natural number or infinity. Okay, in this case, of course, it's going to actually be a natural number. So that must mean that the order of the subgroup does indeed divide the order of the group. We don't end up with a decimal when we do this, or a fraction. Okay, we always end up with a whole number, which means that the order of the group must be a multiple of the order of the subgroup here. Okay, so that gives rise to Lagrange's theorem, just a little reminder there. Okay, so there's the basic definition of the index of a subgroup and some basic results when we're dealing with finite groups. What I now want to look at is a really important result concerning what happens if you have an intermediate subgroup and what you can do in order to work out the index of a subgroup in the group if you've got an intermediate subgroup. So let me explain the setup here. So what we're going to have is, again, we're going to have some group, capital G, and actually this result is going to work whether the group is a finite group or if it's an infinite group. Okay, so again, we're not going to restrict our attention down just to finite groups here, although it would be easier to do so, but we will keep this general. So what we're going to have now is we're going to have a subgroup H, which is of course going to be a subgroup in G, but we're also going to have an intermediate subgroup which I'll call K. So this is the setup that we're going to have. Our biggest group is going to be the group capital G, and then we're going to have two subgroups of capital G. We're going to have the subgroup capital H, but then we're going to have an intermediate one which is K, which completely contains H but is itself a subgroup of G. Okay? Right, so now what is the theorem that I want to show you here? So the claim, and I'll just put this here, so claim that if you want to work out the index of the smallest subgroup here in the group capital G, so if you want to work out the index of H in G, what you can do, this is the claim, is you can work out the index of the intermediate subgroup K in G. So you can work out how many cosets or left cosets does the subgroup capital K partition the group G into, and then you can multiply this by how many cosets would the smallest subgroup capital H partition K up into. Okay, so this is what I want to show is true, and this works whether these indexes are finite or infinite. Okay, this formula still holds true even if some of these are infinite. Okay, and the reason of course is that we will define infinity times any natural number just to be infinity again. So if either of these is infinite, then the other side here will also be infinity. Okay, but firstly let's handle the finite case, because that's the more intuitive case, and then we'll come back to the infinite case. So first let's just get intuition for this result in the finite case. So we're initially going to assume that both of these are finite. Okay, so the index of H in K is finite, and the index of K in G is finite. Okay, and we're going to prove that the result is true if both of these are finite. Okay, so let me try and draw a picture. I think the best way to actually explain why this is true is just with a picture. You can do it by writing stuff down, but you end up having to put in a huge amount of notation, and really the picture, in my opinion, explains this best. Okay, so let's just draw a picture. So firstly we'll draw on our large group, capital G. Okay, so this box, as always, is going to be the biggest group, capital G, and I'll try and stick to the same colours as before. So we'll have it in green here, like so. Okay, and then what we'll have is our smallest subgroup, capital H, but I'm going to again have it partitioning the group into 8 cosets, and I'd like to actually get it done right this time, so I'll draw them first, so that we don't end up with the mess that we had up there. Okay, so that they all look the same size, convincingly. Okay, so here we are. I've partitioned my group into the cosets of my smallest subgroup, capital H here, so I have H in orange here. So this is going to be H down here, and I'll just underline it in orange, and I'll also underline my group capital G in green there. Okay, and this time what's new is that I'm going to have an intermediate subgroup now. I'm going to have K, so let me mark on K. Now K is going to completely contain H as a subgroup. Okay, so I'll mark K on like so, and you'll note that I've done this very particularly. I've got K containing an exact number of the cosets of H in G, and I'll explain exactly why I have to do that in just a moment. Okay, i.e. why I can't just have some random blob drawn on here that contains H. It is a very nicely organised rectangle here that contains an exact number of cosets of H in the group capital G. So this is my intermediate subgroup K here. Okay, right, so firstly let me give the justification for why I have K containing an exact number of cosets of H. K is a subgroup of G. It's a group in its own right, okay? And it's a group in its own right that contains H as a subgroup of K. So imagine for a moment that we get rid of all of G. Imagine that that bit is gone. Okay, now you've just got K here as a group in its own right, existing as a group in its own right, with H as a subgroup. What you could then do is partition K up into the left cosets of H, okay? And you'd get an exact number of them, and that, of course, the value that you get would be the index of H in K. Okay, so you get an exact number of cosets of H in this subgroup capital K. And I hope you understand that those cosets that you partition K up into, if you were viewing it as a distinct object in its own right outside of the group capital G, would be the exact same cosets that you partition it up into if you view it as just part of this larger group capital G, and you're undertaking the task of partitioning the entire group capital G into the cosets of H. So what I'm saying here is that truly it is the case that we can either partition K up into the cosets of H as a group in its own right, okay, separate from the group capital G, or you can firstly partition the entire group capital G into the cosets of H here, the left cosets of H, and then just look at the ones that pertain to the subgroup capital K. Okay, those two ways of doing it, you will end up with the exact same partition of the intermediate subgroup capital K. Okay, so that's why I can truly say that K must contain an exact number of cosets of H, and why I've drawn it in this way. Okay, so now let's get an intuitive feel for this result here. So, we've understood what we mean by the index of H in K. That's just how many left cosets do you partition K up into when you partition it up using this subgroup H. Now let's understand the index of K in G. That's just the number of left cosets that the subgroup K partitions the group capital G into. Now, let's add that onto the picture. So here is the subgroup capital K. So, intuitively, although I will have to just argue this in a moment, what do you think the partition of G up into the cosets of K should look like? Well, intuitively, my best guess would be that it would look like this. So I'll outline them in purple here. So these 4 cosets here would be the cosets of K in G. Okay, so now this is what this means. This means the number of left cosets that K partitions the group capital G into. Okay, so if we now want to construct the number of left cosets that H partitions the group capital G into, then we can firstly find out how many cosets the subgroup K partitions the group into, and then we times that by how many cosets the subgroup H partitions K into. And then the idea is that all of the cosets of K in this partition of G up into the cosets of K are going to be partitioned up into the same number of cosets of H as the actual subgroup K is partitioned up into, and that's why this result is going to hold. Okay, so there's the intuitive reason that this result is going to hold. Now let's actually give the explanation as to why we can truly say this. Okay, so this entirely rests upon then each of these cosets of K. So for instance, let's say this coset of K here, breaking up into cosets of H here, and in particular breaking up into the same number of cosets of H as the actual subgroup K breaks up into. Okay, and that's why this would be true, because then the number of cosets that we'd get of H in G would just be the number of cosets that we have of K in G times how many cosets of H are in each of those cosets of K, okay, which would be this, and that would be why this result is true. But what we need to show is that indeed each coset of K is going to break up into cosets of H and the same number of cosets of H as the actual subgroup capital K. Okay, so let's just take an arbitrary 1 here. So remember what a coset of K actually consists of. So let's take this coset of K here. This is going to consist of some element which will denote A as usual, times all the elements of the subgroup capital K. Okay, so it's going to be the set containing all things of the form A multiplied with little k, where little k is an element of capital K, and I might just write this out. So A multiplied by little k, where little k is an element of capital K here. Okay, now what I'm saying is that we can partition K up into cosets of H. Okay, so I'm going to partition K up into cosets of H. We've already discussed that that is possible, and the number that I will get is this index of H and K. In this case, of course, this is 2 in the terms of our picture. Here's K, and it's clearly partitioned up into 2 cosets of H. More generally, it'll be some finite number, because remember we're assuming that both of these are finite at the moment. So let's call it N. Okay, so we partition up our subgroup K into these cosets of H, and we've got N of them. Now, if we think about this, that means that all of these values, little k, they are now going to be partitioned into n distinct cosets. Before, they were just part of one massive great subgroup here. Now they're partitioned up into the cosets of this subgroup H. So if I draw a picture here to generalize this, okay, let's say that we have pulled out our subgroup K here. Okay, so here is our subgroup K, and I've pulled it out from the group capital G here. Okay, and to make it more general, because in this picture, of course, the index of H and K was just equal to 2. In this picture, I'd like to make it more general, so let's have our subgroup H much smaller now, and let's say it partitions it up into more generally n different cosets. I know this picture shows 5, but more generally it's going to be n different cosets here. So here is our subgroup H. Well now, when we look at these cosets of K that are in the group capital G, these are consisted of A multiplied by all the elements in here, and all the elements in here are now divided into these n different cosets of H. Okay, so hopefully you can now see that actually what we're now going to get is n different cosets of H inside this coset of K, because what we can do is imagine breaking now up this subset here into different cosets of H here. Okay, I can multiply A by all the elements in this coset here, the actual subgroup H, and I'll get a subset of this which will be one of the cosets of H. Then what I can do is I can say another part of this is A multiplied by all of the elements in this coset, and that'll give me another left coset of H, and you can continue on breaking this coset of K up into now cosets of H by breaking up this little k here into the different cosets that we've broken up big K into according to H. So intuitively, I hope that picture explains why each of these cosets of K in the group capital G is going to split into the same number of cosets of H as the actual subgroup capital K splits into. Okay, so truly then, when we actually partition G into the cosets of H, all we need to do is go through all the cosets of K here, partition them all up into cosets of H. Each one of them will split into this many cosets of H. So overall, the number that we're going to have in the entire group is the number of cosets of K in G times the number of cosets of H in K. Okay, how many cosets of H each of these cosets of K splits into. And that is why in the finite case this works, this formula works. Now in the infinite case, where either one of these or both of these are not finite now, so either one or both of these is infinite, then of course we need to alter the arithmetic that we're working with here. So we need to imagine sticking onto the end of the natural numbers this symbol called infinity, and then we'll define infinity multiplying by any other natural number, or indeed by itself, to just equal infinity again, and then this can work. I.e. what this will read is that if either of these is infinite, then this product will still be infinite, and therefore the index of h and g will be infinite. Now why is that true? Well, let's see, if this one's infinite here, that means that if you partition up the subgroup K, the intermediate subgroup, into the cosets of H, you get an infinite number of them. Okay, if you've got an infinite number of cosets of H in K, K is just a subgroup of G. So if you were then to partition K up into cosets of H, you're not suddenly going to get a finite number of them, because all of the cosets that you partitioned K up into as cosets of H will still be cosets of H in the partition of G into cosets of H. Okay, so these cosets will still all be here when you're trying to construct this. So this isn't going to be finite, so this will also be infinite. So the formula's fine if this one's infinite. Now let's say this one's infinite here and potentially this one is finite. Well, if the index of K in G is infinite, that means that the number of cosets of K in G is infinite. Why does that imply that the number of cosets of H in G, where H is a subgroup of K, is also going to be infinite? Well, because each of these cosets of K is going to break up into even more cosets of H. So you can't possibly suddenly end up with a finite number of cosets of H and G, okay, because as I say, the number of cosets of H and G has to be bigger than the number of cosets of K and G, because H is a subgroup of K, and therefore each of the cosets of K is just going to multiply, basically. It's going to break up into loads more cosets of H, so this one cannot be finite either, so again this would be infinite. So this formula here, this multiplicative law for the indexes of subgroups, does indeed even hold true where we're dealing with subgroups of infinite index in groups. Okay, right, so we will end this video here. That rule is extremely important, so that's one of the big take-home messages from this video. Thank you.